Hello everyone, my name is Gerard and I'll be presenting on an ongoing research work on the development of a model for ion crossover in the vanadium redox flow battery membrane. Because of the harmful effects of fossil fuels on the climate, the world is turning into renewable energy for its energy needs. However, intermittency is a major hurdle in the implementation of renewables. This is demonstrated well by the duck curve. For solar energy, for example, supply peaks during the day, which outputs some extra energy that doesn't get used. Then, when the supply gets lower, the demand goes up considerably, which can cause some instabilities in the grid. Therefore, in order to level out this demand, we can look into storing this extra energy in the form of batteries. When we think of batteries, we normally think of these, but batteries come in all shapes and sizes, such as redox flow batteries, which consists of a positive and negative electrode with electrolyte solutions that are divided by an ion exchange membrane. These are very suitable for large-scale renewable energy storage because their energy capacity can be increased by only increasing the electrolyte volume. How it works is that energy is stored by taking advantage of electrochemical reactions of species in a negative and a positive electrode, which goes in one way when the battery is charged and the other way when it is discharged. The membrane is permeable to some non-active ions, which allows for charge balancing. Our flow battery of interest here is the vanadium redox flow battery, or VRFB, which consists of vanadium on both electrodes, taking advantage of the four valence states of vanadium. Sometimes, however, we would have vanadium ions themselves passing through the membrane, which is not good as it causes a loss in the battery capacity and a decrease in efficiency. Since vanadium is the only active species in the solution, the main advantage of VRFB is the fact that crossover doesn't cause any irreversible reactions in the battery, which makes it all the more important to minimize crossover in the membrane to make VRFBs economically competitive. Recently, experimental discoveries demonstrated a decrease in the vanadium crossover and a significant enhancement in the battery's efficiency and power density through the addition of an exfoliated graphene layer to the VRFB's membrane. Therefore, complementary computational work is needed by building a VRFB model that includes crossover mechanisms in order to give further insights into the effects of crossover on the battery's performance, which is the focus of our research. The model development was divided into two phases, what I call the base case model and a reaction case model, building on the model from phase 1 and adding complexity to the crossover reaction, which will be explained later, both following a sequence of modeling, simulation, and verification. The base case model combines several models from literature with equations on 5 domains and 4 boundaries, as shown here, and is a two-dimensional and dynamic model with the following assumptions. For the domains, the current collector was modeled as a simple conductive material, and the negative and positive electrodes and the membranes included relevant equations for electrochemical systems on mass and charge transfer, thermodynamics and kinetics, and fluid transport. For the rest of the model, the following were considered. The electrode-membrane interface in particular is a key boundary when considering ion crossover. For this, fast and non-electrochemical reactions were assumed to happen in the boundary, which is a key assumption for the base model. Simulations are currently being implemented in COMSOL multiphysics with some aid from Python, and a series of simplified tests for separate components of the model are being carried out as shown here. Then, when all of the simplified tests work, a full simulation test will be done to test out the entire model. After this, we hope to move into our verification part, where data from literature and the lab will be used to verify the accuracy of the model. By running simulations on the charge-discharge performance and the capacity of the battery, we expect to have a good agreement between experiment and simulation data. And we will move on to the reaction case model, which will follow the same sequence as phase 1, but will relax the assumption of non-electrochemical and fast reactions at the electrode membrane interface. This will most likely involve further literature review on the information about crossover reactions. Then simulation tests will take place, which we expect to be more challenging, but will hopefully yield results that are closer to reality. This shows the possible future work after the model development. Further analysis will be done, which will bring better insights into the mechanisms of crossover in the VRFB, as well as the effects of membrane enhancements. Ultimately, the hope is that the model will serve as an addition to our toolkit to improve the VRFB performance, promoting it as an economically viable solution for clean energy storage.